Honors Chemistry, this is the lecture video on the first lesson, Math for Chemistry. So what you will do is you can just watch this video, do your assignment as you watch the video. It will give you some sample problems and kind of walk you through just the concepts that we're going to deal with in this first lesson. Alright, so we're going to start with fractions and addition and subtraction of fractions. We don't really do a lot of this in chemistry, but it will come up from time to time, and you should be comfortable dealing with fractions in general. So use the crossing arrows to create a common denominator. So what you do is you take the 2 and you just go over, cross it over to the other fraction and multiply top and bottom by 2. Then 3, you do the same thing. You cross it over and multiply top and bottom by 3. And you just do 4 little multiplications there. 2 times 2 is 4. 2 times 3 is 6, 1 times 3 is 3, and 2 times 3 is 6. So you see that the bottom number, the denominator, is the same, and that's what you need to have to either add or subtract. Now you can ask, is that the same fraction you started with? Is 4 over 6 really the same as 2 over 3? Or is 3 over 6 really the same as 1 over 2? And the way to think of it is, in the case of 1 over 2 or 3 over 6, 1/2 or 3/6, is it's just how many pieces you take. You take a pizza, 2 pizzas that are the same size, exactly the same size. And it's just how you decide to cut them up. So if you take one of the pizza and you cut it into, just right down the middle into 2 pieces, and you eat one of those 2 pieces, you've eaten half the pizza. If you take the other pizza and you cut it up into 6 different pieces, and you eat 3 of those 6 pieces of pizza, you've eaten the same amount of pizza. All that was different was how many times you decided to cut the pizza, but in both cases you've eaten half of the pizza. So yes, those 2 numbers are the same. The 1/2 and 3/6 are the same. The 2/3 and 4/6 are the same number. Okay, so you add those. You only add the numerator, the top. You don't add the denominator. So it's 4/3. 4 plus 3 is 7, and the 6 stays the same on the bottom. For subtraction, it's the same thing. You take the 3 over top and bottom, take the 5 over to the other side, top and bottom, do 4 little multiplication problems, and you get 9/15 minus 5/15, and that would equal 4/15. So that's how you add and subtract fractions. Okay, multiplication. Multiplication, multiply the numerator and the denominator. In this case, you do multiply both. So you multiply the numerator straight across, so 2 times 4, and the denominator straight across, so 3 times 5, and that would give you 8 over 15. Sometimes students confuse multiplication of fractions with proportions. You do not cross multiply. That's a proportion. That would be like 2 over 3 equals x over 14. And then you cross multiply and divide to find the value of x. But that's not what we're doing here. We're just multiplying fractions. So straight across, top and bottom, just like that. Now, it's possible, simplify the fractions before multiplying. So in this case, we have 3/8 times 4/9. You can cancel across a multiplication sign. You can't do it across an addition, subtraction, or division sign, but you can cancel across a multiplication sign. So the 3 and the 9 can cancel. So the 3 goes into 3 one time, it goes into 9 3 times. And then the 4 and the 8 can cancel. 4 goes into 4 one time, and it goes into 8 2 times. Now you go ahead and multiply straight across. 1 times 1 is 1. Or just go ahead and rewrite it. 1/2 times 1/3. 1 times 1 is 1, and 2 times 3 is 6. If you had done that problem without canceling, you would have had 3 times 4 is 12, and 8 times 9 is 72. 12 over 72, then you'd have to reduce that fraction down, and it would reduce down to 1/6. All right, multiplication of fractions and integers. Convert the integer into a fraction by placing a 1 in the denominator. So if we have 2/3 times 4, we can simply turn the 4 into a fraction by doing that, 4 over 1. And now if you can cancel, but there's nothing to cancel there. So we're just going to go ahead and multiply straight across, and you get 8 over 3. When the number on the top, the numerator, is larger than the number on the bottom, that's called an improper fraction. And as far as I'm concerned, you can leave it like that, because if you're going to do further math on that fraction 8/3, it has to be as either a proper or improper fraction. Proper means the number on top would be smaller. You cannot have a mixed fraction. Mixed fractions are okay for a final answer. In fact, you should learn how to do them, because on standardized tests, they'll give you your choices will probably be in mixed fractions if it's a fraction problem. But for actually doing further math on that number 8/3, you would have to leave it like that. Don't convert it to, in this case, it would be 2 2/3. You don't want to make that conversion. But we'll show you how to do that here. So convert an improper fraction to a mixed fraction. So an improper fraction has a numerator larger than the denominator. So 5/3. So the way you do that is a simple division problem. So 3 divided into 5. Now there's 3 ways you can express a remainder in a division problem like this. The first way you probably learned was to just put an R for remainder and then whatever the remainder is. The way we generally do it in science is we express numbers as decimal numbers. So it would be, the answer would be 1 point, in this case 6.6 or 6.7. Or you can express it as a fraction, and that's what we want to do here, because that's what we're talking about, a mixed fraction. So 3 goes into 5 one time. 1 times 3 is 3. You subtract the 3 from the 5 and you get 2. And now you're done with the division. So now you have to convert it into a mixed fraction. Mixed fraction means it has a whole number, an integer, and a fraction. So what you're going to do is the number up on top, the quotient, which you obtained from this division, is going to be 1. And then you take the remainder 2 and put it over the divisor. That's the number outside the bracket, 3. So it's 1 2/3. So that would be how you would express that as a fractional remainder, and that's a mixed fraction. You can go in the other direction. There's the remainder over the divisor. Yeah. You can go in the other direction. Let's take the 1 2/3 and go backwards. So the way I teach it is, it's the round the world method. You start at the 3, you multiply that by the whole number, 3 times 1. Then you add the 2, and then you put whatever you get from that over the denominator there, over 3. So we have 3 times 1 is 3, plus 2 is 5, over 3, and that gives you 5/3. And that's how you go in the other direction. Again, if you want to do math on this number further, you can't do it as 1 2/3. You have to do it as 5/3. You have to convert it to 5/3 before you actually multiply it or subtract or do some other math operation on that number. Division of fractions and integers. So here's division of fractions first. So you've probably learned something like keep, change, flip, or when I was in school it was called invert and multiply. You turn it over. So you take the bottom and you invert it. You flip it. So instead of 4/7, it's 7/4. You don't change the numerator. It's still 2/5. Okay, and then now if you can cancel if you want, or just multiply across. I didn't cancel in this case, so it's 14/20. Since they're both even numbers, you can reduce that down by dividing both of them by 2, and you get 7/10. Why does this work? It works, think of this. What is 6 divided by 3? Let's do 6 divided by 2. What's 6 divided by 2? It's 3. What's 6 times the reciprocal of 2? Well, first of all, what's the reciprocal of 2? The reciprocal of 2 is when you flip 2 over, that's 1/2. So 6 times 1/2 also equals 3. So 6 divided by 2 is equal to 6 times the reciprocal of 2, 1/2. Both of them give you 3. So multiplying by a reciprocal is the same as dividing by a number. Okay, for integers, you place a 1 underneath. So here we have 2/3 divided by the whole number, or integer number 4. Whole number, by the way, is a number 0, 1, 2, 3 going in the positive direction only, not negative numbers. Integers are negative numbers as well. Okay, so you're going to just turn that 4, one additional step here, turn it into a fraction by putting a 1 underneath it. And now you flip the bottom and multiply. So 2/3 times 1/4 is 2/12, and then you can reduce that down to 1/6. Same thing if the whole number is on the top, 6 divided by 2/5. Turn the 6 into a fraction, flip the bottom, multiply, and there you get the answer. Okay, units of measurement can be canceled in the same way as numbers or variables. Treat numbers and units that are not in fraction form as though they are in the numerator. And so you'll see an example of that here coming up. So a unit of measure is simply the word or abbreviation that comes after a number that tells you what it is. So I used the example in class. If I tell you that we're at Hoover and there's 10 outside in the parking lot, you're going to want to know 10 what? What does the 10 mean? Just the number 10 doesn't give you the information you need. You know, could be 10 cars, could be 10 people. So the unit of measure is the word cars or some abbreviation for that, or the word people or some abbreviation for that. That's called the unit of measure. It's what your number is measuring. Okay, so here we have one that you'll see in this class quite a bit. It's moles per liter. You don't have to understand what that means right now. Just understand it's a unit. It's a combined unit of measure. It takes two different units of measure and puts them together into moles per liter, moles over liters, and you're going to multiply that by 4 liters. So the numbers you would simply multiply. So the 4-liter term is in the numerator, so that's what I was referring to earlier. It's just on one level. There's not a top or a bottom. You assume it's in the numerator, it's on the top, that there's a 1 down there on the bottom that you don't have to write. Over 4 liters over 1, you don't have to write that. Okay, so it's on the top. So what you're going to do is you're going to put that 1 down below there just for the illustration, but you don't have to do this. And what you see is you're going to get is 3 times 4 is going to be 12. But the liters cancels. You can cancel those just like we canceled numbers in the fractions. Or just like you could cancel the variable x in an algebra equation in math class. Okay, so the liters cancel, so the only thing you have left is moles. And so you get 3 times 4 is 12. Just go ahead and do the math, and it gives you 12 moles. So we can cancel units of measure like that. For integers, place a 1 under the integer to create a fraction, then flip the bottom and multiply. So this one looks a little tricky. But again, what you can do is put a 1 underneath the 12 there and a 1 underneath the 2. So now you have them both looking like fractions. The one on the top is simply moles on the top and nothing on the bottom. The one on the bottom, though, has 2 different levels to it already. It had moles over liter, so 2 moles over 1 liter. Okay, now you can flip the bottom, and there it is. And now you can cancel the moles, moles on the top, moles on the bottom there. And so your answer is simply, the unit of measure for your answer is going to be liters. The moles canceled out. And so it's now 12 divided by 2, which is 6. So your answer would be 6 liters. All right, so let's go ahead and do a simple problem here. How many centimeters in 4.5 meters? So to convert, you must know the relationship between centimeters and meters. And that relationship is there's 100 centimeters for every 1 meter. So what that simply means is you can either say that there's 100 centimeters for every 1 meter, or you could turn the sentence around. You could say there's 1 meter for every 100 centimeters. Those are both true statements. So that's what the ratios down below are saying. So this can be expressed in 2 different ratios. There's 1 meter, the one on the left is red, there's 1 meter per 100 centimeters, or there's 100 centimeters per 1 meter. Those are both true statements. But only one of them is going to help us solve this problem. So again, we'll choose one of these to go into the equation. Okay, so the relationship between meters and centimeters is 100 centimeters to 1 meter. So this can be expressed as 2 different ratios. So the question mark means which one do we choose? Which of these 2 ratios do we choose? Only one will work in this problem. So we're starting with 4.5 meters. What we want is to find out centimeters. That means that meters needs to cancel out and centimeters needs to appear on the top in our final answer. So which one of these 2 would make it do that? The first one or the second one? The answer is the second one. That there's 100 centimeters for every 1 meter. So what that means is you're going to cancel the meters. Meters cancels with meters, and you end up with only centimeters at the end. And now once you do that, you do the math. It's 4.5 times 100, and that's going to give you 450 centimeters. Now, this is a problem. You may say to yourself, well, I could kind of do that in my head, but believe me, in this class, we're going to get into problems like this that you cannot do in your head. In fact, you will not have any clue how to solve them unless you know how to set up the equations like this. And so please learn that when I ask you to do these problems, it's very important that you lay them out like this. I don't want to just see an answer. The answer is the least important part. It's seeing that you know how to lay out the equation and cancel the units properly is the important thing. You've got to learn how to do that, or you're really going to be lost when we get into some a little bit more complicated chemistry problems that involve this concept. Okay, so units of measure are essential in chemistry and other sciences. Units of measure are the word or abbreviation that comes after the number to indicate what you are dealing with. So there's our example again. If I say to you, do you want 10? You respond, 10 what? 10 pizzas? 10 books? What are you talking about? In this example, books and pizzas are the unit of measure. They indicate to what the number is referring, to what object, to what thing the number is referring. Okay, so here are some of the more common units of measure that we're going to be dealing with in chemistry. Grams is fairly small. If you've seen a large paper clip, you know the two different sizes, one's a little bit larger than the other. The larger one is exactly 1 gram. So if you want to know what a gram feels like, that's 1 gram. A liter, you all know what a liter is. You probably bought water or soda or something in a 1 liter bottle, so you have a sense of what that is. Meters is a common one. By the way, in the first one, mass, grams, generally in physics we talk in terms of kilograms because we're talking about life-size objects, things that are fairly big. A kilogram is about 2.2 pounds, a little more than 2 pounds. But in chemistry we're dealing with smaller measures usually, so we deal in grams. Meters, and there's all kinds of subunits of meters, millimeters, micrometers, nanometers, so we'll be dealing with that quite a bit. Time is universal, whether you're on the metric system or the English or imperial system that we use here in the United States. And metric system is the one we use in this class, though. That's time, and so time, seconds, minutes, hours. It can also mean calendar time, days, weeks, months, years, but generally not in this class. Temperature. We don't usually talk in terms of, in fact, almost never, the Fahrenheit system that we use. So somebody tells you the temperature outside right now is 70 degrees. That's in Fahrenheit. We never use that in chemistry. We either use centigrade or Kelvin, and we'll talk about those at a later time. And joule, it's the standard unit of measure for energy. And that's really the one unifying thing across science is energy. So electrical energy can be measured in joules. It can go through a light bulb and be converted into light energy and heat energy, and both of those can be measured in joules. When you drop a rock off a building, like you might have an example like that in a physics class, that energy, potential and kinetic energy, is measured in joules. So this idea that there's all these different things that seem like they're totally different from one another, electricity, light, heat, the motion of a rock falling from a building, they all seem totally different, and yet they all have this common element called a joule, energy rather, which is measured in joules. So you'll see joules quite a bit coming up. Okay, so these prefixes, words that come before, can be placed in front of a unit of measure, what we just saw in the last slide, to assign number values. So you've heard of some of these before, some of you haven't. But the ones on the top are really big numbers. Tera is a trillion, giga is a billion, mega is a million, kilo is 1,000, hecto is 100. It's never used. You never hear that. And when I say never used, it's never used in chemistry. Deca is pretty much never used either. Now you get down to, in the middle, you see just 10 to the 0, which is equal to 1. And so that would be whatever we're talking about, a meter, a gram, whatever. Okay, and then the ones that are less than 1, it doesn't mean they're negative numbers. It just, a negative exponent just means it's a number between 0 and 1. It's a positive number between 0 and 1. So that's deci. We don't use that one a lot, but centa we do a lot. Centigram, centimeter, millimeter, micro, is 1/1,000,000th, milli is 1,000th, micro is 1/1,000,000th, nano is 1/1,000,000th. We use that a lot with light when we talk about light energy. And pico is 1/1,000,000,000th. Sometimes we talk about that in terms of picometers, in terms of the distance across atoms or something of that nature. Okay, so a prefix symbol such as that letter, funny letter, is mu, micro, n, nano, or k, kilo, in front of a unit of measure indicates a power of 10 to be multiplied by the number in front. Here are some examples. Okay, so 6.7 microcoulombs would be 6.7 times 10 to the negative 6th coulombs. The reason you need to know how to do this is because if you want to work with that number in an equation, you're going to have to know how to convert it to scientific notation like that. And there's the actual decimal notation of the number over there, and we'll talk about scientific notation and that conversion in just a minute. 430 nanometers, that's a number you come across in measuring the wavelength of a light wave, and so that would be 430 times 10 to the negative 9th. And 230 kilojoules, and kilojoules is a unit that we use a lot when talking about heat going into or coming out of a chemical reaction, and that would be 230 times 10 to the third, or that's 230,000. Okay, now let's get into scientific notation. You're really going to have to become kind of adept at this. It's not that hard, it just takes a little bit of practice. Okay, so scientific notation is a way to convert very large or very small numbers to a shortened length. So the speed of light that you learned about in physics class is 300 million meters per second. But that's kind of a long number to write, and believe me, there's numbers much, much longer than that we use in chemistry. So in scientific notation, it's 3 times 10 to the 8th power. That means the 8 would tell you how many zeros there are behind that 3. Okay, so it's just a shorter way to write long, very large, or very small numbers. The parts of scientific notation are 3 times 10 to the 8th. That's the coefficient, the number out front. That's the base 10, and we always use base 10 in scientific notation. And finally, the exponent, and that's to the 8th power. Okay, so converting from decimal to scientific notation. So move the decimal to form a number between 1 and, I have to say 9.9999999. You can't say 1 and 10, but between 1 and 9.999. So count the number of places the number was moved. If the original number was greater than 1, the exponent is positive. If the original number was less than 1, the exponent is negative. So let's just see some examples here. By the way, note a negative exponent does not mean a negative number. It is a positive number between 0 and 1. If it's a negative number, it'll have a negative sign out in front of the entire number. I'll show you that in a sec. Okay, so convert from decimal to scientific notation. So the first thing, a comma is for readability only. It can be removed. And by the way, that's not true in many other countries. Many other countries, the comma is used the way we use a decimal point, and you couldn't just take it out. But in the United States, a comma is just to make the number more readable, long numbers readable. You put a comma every 3 digits in very large numbers, but it's not a decimal point. It's not the same. So place a decimal at the end of the number. So right there. So as we take away the comma, it's 67,700. Move the decimal to form a number between 1 and 9.999. Count the number of positions the number was moved. So right there, we move the decimal over, and the number that we could form between 1 and 9.999 is 4.67. That's a number between 1 and 9.99. Okay, so we've done that, and then we count how many places did we move the decimal. The decimal is moved 4 places, and the original number is greater than 1, so the exponent is plus 4. You don't have to write the plus sign, but just for emphasis, it's positive 4. So the number in scientific notation will be 4.67 times 10 to the 4th. Do you have to write those 2 zeros that were at the end once you get there? That gets into a concept called significant figures, and the answer is it depends. It depends how precise your measurement is. We're not going to talk about that today, though. So For right now, we'll just say that you can drop those last two zeros there, okay? So that's how you would make that conversion. Okay, converting from decimal to scientific, let's do it with this number. So move the decimal to form a number between 1 and 9.9. Count the number of positions. So there we do it right there. So 8.2 is a number between 1 and 9.9. And we moved it. The decimal was moved 3 places, and the original number is less than 1. It's not a negative number, but it's less than 1. So the exponent is -3. So that means our scientific notation will be 8.2 times 10 to the -3rd power. And again, note a negative exponent does not mean a negative number. It is a positive number between 0 and 1. If that were a negative number, you would put the minus sign out in front of the -8 of the 8.2. So it would be right out in front of the entire number. Negative 8.2 times 10 to the -3rd would make that a negative 0.0082. Okay, now we're going to go in the other direction, converting from scientific notation to decimal. So there's a scientific notation number. So write the coefficient by itself and move the decimal the number of places of the exponent and fill the blank spaces with zeros. So we're going to write 6.7, and you see that we have an arrow moving to the right, and it leaves these two little blank holes right there. I call them an egg carton, and you're going to put eggs in the egg carton. So the exponent is positive, so the number will be greater than 1. If we had gone in the other direction with the decimal point, you would have ended up with a number less than 1. But since the exponent is positive, it's got to be a number greater than 1. That means you're going to move it to the right. So there's the number right there. You filled in those two empty spaces with zeros, so you get the number 6,700. The decimal can be eliminated if there are no digits to the right of it. Now, that will, again, significant figures, that concept might have something to say with that. But it's very rare that you write a decimal point when there's not any digits to the right. It's very rare. It can be done, and again, it has to do with significant figures, so don't worry about that right now. Okay, let's do the same thing here. 2.1 times 10 to the -4th. Write the coefficient. There it is. And since it's a negative exponent, it means it's going to be a number less than 1. That means you're going to have to move the decimal to the left in order to get to a number less than 1, a positive number less than 1. So I moved it 4 spaces. You can see there's 3 little slots there to fill in with zeros. So you get 0.00021, and that's the answer. The exponent is negative, so the number's between 0 and 1. And there it is. A leading zero should be placed to the left of the decimal. That zero that is to the left of the decimal is called a leading zero. It's just done. It's just the way it's done. It doesn't change the value of the number. What it does is it indicates kind of that there is a decimal point there and that there's nothing to the left of the decimal point other than there's just nothing. There's 0, okay? So you just, by convention, by tradition, you write that 0 there, but it does not change the value of the number. Okay, now we're going to multiply. Multiplying is pretty simple. Multiply the coefficients and add the exponents. That's all there is to it. So you take those two numbers, you multiply 4.1 times 1.8, and you add 7 plus -2, or you can say 7 minus 2, but it's 7, you're adding those two numbers. 7 plus -2, and that gives you 4.1 times 1.8 is 7.4, and 7 minus 2 is 5. So that's how you do a multiplication in scientific notation. Okay, how about this one? So you multiply the decimal. Now you don't have two numbers in scientific notation. You just have one of them is, and the other one is just 3.6. So all you do is you treat that like a coefficient. Really, you could write 3.6 times 3.6 times 10 to the 0 power, because 10 to the 0 power equals 1, and 1 times 3.6 is 3.6. But you don't need to do that. That's just unnecessary work. So just remember that if you just have a number multiplied by a scientific notation number, you just treat it like a coefficient, and you don't have to mess with the exponent, the 10 to the -6 part. Well, maybe you don't. We'll talk about that. So 3.6 times 2.3, you just simply multiply those, and it gives you 8.3 times 10 to the -6th, and that's how you do that. Okay, now we're going to get into just another little twist of doing this. It's not terribly complicated, but you should remember this. Okay, so we're going to multiply these two numbers. So multiply the coefficients and add the exponents. And what you'll end up with here is 11.96 times 10 to the 5th. Okay, and there's a reason why I put those two zeros after each of the coefficients, and again, keep hearing me say this. It has to do with significant figures, but we're not going to worry about that now. So it's 11.96 times 10 to the 5th. Now, by convention in scientific notation, almost always, and you'll learn one of the exceptions later on in this course, almost always the coefficient should be, as we said, a number between 1 and 9.9. 11.96 is not between 1 and 9.9. So what we're going to do is we're going to make it a number between 1 and 9.9 by doing the following. We're going to move the decimal to the left, so it goes from 11.96 to 1.196. Now you can't just move a decimal like that unless you make some other adjustment. You don't want to change the value of the number. So look at that coefficient. We made the number smaller. We went from 11.96 to 1.196. So to compensate for that, and so the number doesn't change its value, we have to take the exponent and make it one place bigger. So it goes from 5 up to 6. And so 11.96 times 10 to the 5th is exactly the same number as 1.196 times 10 to the 6th. Mathematically, when you move that decimal over in the coefficient, you're dividing that number by 10. 11.96 divided by 10 equals 1.196. And when you increase an exponent of base 10 by 1, you're multiplying by 10. So going from 5 to 6 is 10 times greater. So you've divided one of the numbers by 10, and you've offset that by multiplying the other number by 10. And so those two numbers are of the same value. But in scientific notation, you should, as I say, except for one exception we'll talk about later in the course, you should move that decimal place over. So move the decimal to the left on 11.96, making it 1.196. Then the exponent becomes bigger from 5 to 6. Okay, so it's a pretty easy concept. It can also go in the other direction sometimes. The coefficient has been made smaller by one place, so the exponent must be made bigger by one place. The two numbers above have the same value. If you make the coefficient bigger, then the exponent must be smaller. If the coefficient is made smaller, then the exponent must be made bigger. All right, divide the following scientific notation numbers, divide the coefficients, and subtract the exponents. So 5.2 divided by 2.5, you divide those two, and then it's just the opposite of doing multiplication. You subtract the exponents, the top one minus the bottom one. So when we do that, no decimal adjustment is needed in this case. It could be, but not in this problem. You get 2.1 for the coefficient, and you get 6 minus 2, which equals 4 for the exponent. So the answer to that would be 2.1 times 10 to the 4th power. Okay, very rarely do you add or subtract scientific notation, but you should know how to do it in case it comes up. So here we have two scientific notation numbers, and we're adding them. We're not multiplying them, we're adding them. So in order to add scientific notation, you must have a common base and exponent. In other words, the base is always 10, so you don't have to worry about that being common, at least in this class. Math class could be different. But the exponent also has to be the same. And you see that one of the exponents is a 3 and one of them is a 4. So what we need to do is adjust the decimal on one of the two. It doesn't matter which one, but one of the two must be adjusted so that we can change the exponent so that they have the same exponent. So a common base and exponent can be created by moving the decimal to the left on the 5, making it 0.5. So on that left number, we're going to move the decimal over to the left, so you get 0.5. Then the exponent increases from 3 to 4. So in other words, we made the coefficient smaller by going from 5 to 0.5. Therefore, you must make the exponent bigger by going from 3 to 4. Now you can see that both numbers have a common base and a common exponent, 10 to the 4th. Now that they have that, you can go ahead and add the two coefficients. So 3.7 plus 0.5 gives you 4.2, and then the base and exponents stay the same, 10 to the 4th. Now at that point, you might, have to adjust the decimal again. If I had decided to move the decimal on the 3.7 to make that 37 times 10 to the 3rd, I would have ended up with a different number, and I would have had to adjust the decimal. But we didn't need to do that here. So anyway, don't worry about that. Okay, so that is the end of this lesson. And you really should be able to do all of the problems based on this with a little practice, but I will go through and answer some of them, not all of them. And then, of course, go ahead. Part of this assignment is to watch that very short video from Eli Lilly Company about breast cancer medications or treatments, and just write a short paragraph. I'll give you a little time in class with your group to work on these problems together. But try to get them done as much as possible at home, and then just bring the ones that you couldn't do to your group, and you can share out there. Okay? All right, so I'll see you on the answers video for this particular lesson in just a little while. Have a great day.